I'm Matthew Sandoval, and this is Lab 1, Constant Velocity. There are 5 parts to this lab: the introduction, the experiment, the code, discussions, and conclusions. The purpose of this lab is to use Newton's first and second laws on a real-world example in order to illustrate the concept of constant velocity. It can be concluded by the end of this experiment that Newton's laws do apply to the real world, but various forces prevent an adequate viewing of the laws in action. So there are 3 fundamental physical principles that will be used in this lab: constant velocity, Newton's first law, and Newton's second law. In order for an object to have constant velocity, the net force acting on the system must be 0. This is derived from Newton's first law, which states that an object will stay at motion or rest unless an outside force acts upon it. This allows us to see that constant velocity will remain constant unless there's a net force greater than 0. Newton's second law, in simple terms, states that force equals mass times acceleration. Because constant velocity requires a net force of 0, this means the acceleration of the system must be 0 since there cannot be 0 mass. There are 3 required formulas for this lab: average velocity, position update, and velocity update. All 3 of these formulas will be used to calculate components in the computational part of the lab. For the experiment of this lab, I rolled a portable charger over a dresser. The dresser was 24 inches in width and had a slight decline, which will come into play later. I then uploaded the video to Tracker, which allowed me to plot how the charger moved and track its motion. Using starter code and values derived from Tracker, I was able to make a GlowScript program that illustrates the predicted constant velocity of the charger. I then took values from both Tracker and GlowScript and plugged them into a Google Sheet in order to graph predicted motion and the observed motion of the charger. Every experiment has a system and a surrounding. The system is the thing you are observing, and in this case, the system is the battery. The notable surroundings of the system are the dresser, friction, gravity, me, and the wall. Although for this experiment, it is to be assumed these forces are not acting on the system as to achieve constant velocity. Because constant velocity requires no net force acting upon the object, if these surroundings were present in the experiment, then the data could be skewed. The initial conditions of the experiment were found using appropriate formulas and data recorded in Tracker. The observation start time was 0 seconds. The initial position occurred at that x component and 0, 0 on the z component. And the battery's average velocity, which required me to use a time and position on Tracker besides the initial time and position, is shown by that velocity average equation below. The time of last observation, which is when the video ends, is 2.802 seconds. So after recording the video, I uploaded it into Tracker and was able to set up an axis that would show the charger rolling in the negative x direction. This gave me a negative velocity and a negatively sloped graph. The graph shown on Tracker indicates very roughly constant velocity, as it is more or less in a straight line. While the code for GlowScript was a starter code, there was plenty I had to change in order to make it fit my experiment. The first thing I had to change was the mass of the ball. GlowScript uses kilograms, and the mass of my item was 136 grams. Therefore, it was 0.136 kilograms on GlowScript. The next section I had to change were the initial values for position and average velocity, which I found in the previous slide on Tracker. The next portion I had to change was the while loop. By changing the while loop to end when the time is greater than 2.802 seconds, which is the time that the Tracker video ends, the computational model is now more proportional to Tracker, as both models will depict the same period of time. I changed the fnet to 0 because there should be 0 force acting upon an object in order for it to have constant velocity. The final 2 arrows depict the position and velocity update formulas. These formulas allow the computer model to constantly track where the ball was going to go until the time ended. After obtaining the data from both Tracker and GlowScript, I uploaded it into a Google Sheet and was able to create this chart, which predicts the observed motion and the predicted motion over time. The predicted motion is a red straight downward slope, which corresponds to the constant velocity in the negative x direction. The observed motion is curved and travels much farther than the predicted motion. These differences are due to the surroundings of my system. In the computational model, there are no surroundings, thus the system will move with a constant velocity forever. In the observed model, the slant of the dresser allowed the battery to increase velocity slightly until it hit the wall, thus ending its motion. Both models do begin similarly though, and if it were not for the surroundings, the principle of constant velocity would have ensured the battery would travel similarly to the computational model. As with every experiment, it is important to note that the significant differences presented could be various sources of error. Both the software Tracker and the GlowScript code were complex and had much room for slight error. Measuring inequalities and video distortion could have also affected the results of the experiment. Rounding it out, there are two important questions I need to address. What if I flipped my axis? My charts would, instead of depicting a negative slope, depict a positive slope. There would now be a positive velocity, but speed would remain the same, and the distance covered would remain the same. The final question that must be answered is it possible for me to say how many forces were added together to give me a zero net force? It's possible to theorize and predict, but it's not possible to say exactly how. There's simply not enough information. If it were to have zero net force, possible forces acting on it could include my initial push, gravity, the air circulation of the dorm room, and friction.